So let's talk about the geometric interpretation of average rate of change. So basically, kind of like I drew on the last page, you have some curves. So the black line here is the curve that we're looking at. And we want to find the average rate of change between these 2 points. And so what we're doing, like I said before, we're drawing a line between those 2 points and finding the slope of that line. And so that's, in this particular case, it's called the secant line. We're going through 2 points on a curve. And so that's really all we're doing with the average rate of change. So let's look at this example. We'll see kind of where this is going to lead us in the next couple of weeks. So we have a ball dropped from observation deck, 450 meters above the ground. The distance fallen is given by this formula, 4.9 t squared. Estimate the speed of the ball after 5 seconds. And so kind of what we've done, and we'll work out the first one, and then you can check the rest if you want. But if we want to look at the average rate of change between 5 and 6, that would of course be S of 6 minus S of 5 over 6 minus 5. And so we plug in 6 to the formula. We get 176.4. And then we plug 5 into the formula. And we get 122.5. And then, of course, the bottom is 1. We subtract those, and we get 53.9, which is what we have there. And you could test these out, and you can kind of see. So you can see that we get these. But what you want to observe is what's going on here is this is always starting at 5 and then moving out some measure of time above 5. And you can see it's getting closer and closer to 5, to where when we get right here, we are 1/1000th of a second apart. And so the slope of that secant line is 49.0049. And you can kind of see, aside from this one, but even this follows the pattern, we're getting closer and closer to 49. And so probably what would happen if we could find the slope of the line between, or we can say the tangent line at 5. So let's say that's 5. What would be the slope of that line? It would be 49. We can imagine. And so that's kind of what we're doing. We're going to talk about the secant line between 2 points, 2 arbitrary points maybe, but we're going to shrink that down to where we're just looking at not the secant line anymore, but that would be the tangent line, because the tangent line just touches in 1 point. So let's kind of look at another example here. So you have the height in feet of a baseball is given by 36t minus 16t squared. So let's look at between 0.5 and 1, and then 0.9 and 1, and then 0.99 and 1. And we could do 0.999 and 1 if we wanted to. So let's do this one. So this would be h of 1 minus h of 0.5 over 1 minus 0.5. And so that would be 20 minus 14 over a half. And so that would give us 6 over a half, which is 12. Then let's do 0.9 to 1. So we have h of 1 minus 0.9 over 1 minus 0.9. And so we have 20 minus, and then h of 0.9 is 19.44 over 0.1. So that'd be 0.56 over 0.1. So that would give us 5.6. And then do the same thing with 0.99. So h of 1 minus h of 0.99 over 1 minus 0.99. And so we get 20 for h of 1. H of 0.99 is 19.9584. And then the difference on the bottom would be 0.01. And figure that out, and we get 4.16. And so we can kind of see, maybe not as dramatically as the other one, but we can kind of see we're getting closer to 4, and maybe let's do 0.99 or 0.999 just to see where that goes. Because the next part is estimate the speed of the ball after 1 second. So we kind of need to get as close as we can. So let's see what happens here. So we have 20 minus 19.99598.4, and then that's over 0.001. And so then that comes to 4.016. And so we can see we're kind of getting closer and closer to 4. And you can imagine, judging by this pattern, that possibly if we did 0.9999, we're just going to be adding zeros, maybe. But let's estimate the speed of the ball, since we're getting closer and closer to 4, as speed of the ball after 4 seconds, or after 1 second would be this feet per second. So height is measured in feet, and then time is measured in seconds. And that's the basic idea. So we're looking at the average rate of change and just kind of shrinking that interval down, and then we can make a guess, a reasonable estimate for the instantaneous rate of change.